Hi everyone, I am back for another video. Welcome to lesson 2.9, halogen derivatives. Again, this is adapted from the PSHS LG 2.9. Our target for this lesson is to familiarize with the physical and chemical properties of halogen derivatives or halogenoalkanes. To start, have you ever considered what prevents the sunny side up fried egg from sticking to the Teflon-lined pan? Did you know that the sweetener Splenda, a sucralose, contains 3 chlorine atoms in its structure? And are you aware that the characteristic scent of the ocean is partly due to the presence of haloalkanes in seaweeds? So a haloalkane or an alkyl halide has the formula Rx, where R is the hydrocarbon part of the structure and X is the halogen. So it is expected that the Rx molecule is polar, or at least the Rx part of the structure, Cx part of the structure is polar, and it does not exhibit hydrogen bonding unless, of course, there are other functional groups capable of producing hydrogen bonding in the structure. And also, they're generally insoluble in water and soluble in organic solvents. So the boiling points and melting points of alkyl halides increase with increasing halogen size. That means from fluorine, chlorine, bromine, iodine, and astatine bonded to an R group, which forms the alkyl halide. So boiling points and melting points increase with increasing halogen size. Also, these properties increase with increasing alkyl chain length. That is because as the alkyl chain length increases, the molecular weights increase, and of course, there's greater surface area in general for more London dispersion forces or as well as IMF in general. So resulting to a higher boiling point and a higher melting point. In general, alkyl halides have higher boiling and melting points compared to alkanes. Alkyl halides are classified based on their degree of substitution on the alpha carbon and also based on their proximity of the halogen atom to the pi bond. So let's take a look at these different classifications of alkyl halides. First, we have the methyl alkyl halide. That's the simplest alkyl halide, only bonded where the halogen is bonded only to one carbon. A primary alkyl halide where the halogen is attached to an alpha carbon, which is bound only to one other carbon. A secondary alkyl halide is where the halogen atom is bound to an alpha carbon bound to two other carbons. And for a tertiary alkyl halide, again, the halogen is bound to a carbon, to an alpha carbon bound to three other carbons. Also, based on proximity of the halogen to a pi bond, so here we have the vinylic structure, we have the aryl structure where the halogen is directly attached to a phenyl ring, the allylic structure, and the benzylic structure where the halogen is attached to a carbon that is attached to a phenyl ring. So haloalkanes have both an electrophilic site, usually found at carbon, because in the carbon halogen bond, so the electron density is mostly concentrated towards the more electronegative halogen part, leaving carbon partially positive, making it electrophilic. And then there's an electron-rich site which is X corresponding to the halogen. So the highly electronegative halogen draws electrons towards itself, leaving the carbon partially positive. So this is how it's represented using Lewis structures, Vesper structures. And here's the illustration showing the electron densities. So the halogen is partially positive in this structure. So with this kind of structure, the electrophilic C now can react with Lewis bases and Bronsted-Lowry bases. Remember that an electrophilic particle is attracted towards electrons, while Lewis bases and Bronsted-Lowry bases, well, Lewis bases, as we know, are electron rich, and they would be a perfect pair for an electrophilic carbon, while Bronsted-Lowry bases would have the similar property, except that by definition they're just proton acceptors. So the electron-rich yet electronegative halogen, on the other hand, could detach from the carbon from their covalent bond and remain stable. So in a reaction, they would become the leaving group. So haloalkanes may undergo two types of reactions, substitution and elimination. In the substitution of haloalkanes, so here we have an example. An Rx structure reacts with the nucleophile, and the nucleophile replaces the halogen X in the structure. And then the CX bond, which is a sigma bond, is broken, and a C nucleophile sigma bond is formed. In the elimination reaction of haloalkanes, so we have the Rx group here reacting with the base. So the H and X are detached with the aid of a Bronsted-Lowry base B. So that's B here. And the CX and CH sigma bonds are broken. So these bonds here are broken, and a new pi bond is formed. So here's the pi bond that is formed. Notice that before and after the reaction, the two carbons here still have 4 bonds around them, also 4 bonds around them, and X leaves while B attaches itself to the proton. So those are the two possible reactions that haloalkanes may undergo. So for the navigate part of this lesson, we're asked to classify each halide bonded to an sp3 carbon as primary, secondary, or tertiary. Where applicable, label each halide as vinylic, allylic, benzylic, or aryl. So here, for the first structure, we have 4 halogens in the molecule. So notice that for both bromine atoms, they're attached to a carbon, attached to 2 other carbons. So they're of the secondary type and also allylic, because there's a double bond. There's a double bond on the carbon after the alpha carbon. And then for the chloride parts of the structure, they're primary and allylic. That's because they're attached to a carbon, attached to only one other carbon, and similarly, the carbon coming next after the first carbon has a double bond. And then for the second structure, we only have 1 halogen. Notice that this carbon is attached to two other carbons, therefore making the structure secondary. And we cannot classify it as vinylic, allylic, benzylic, or aryl. Simply a secondary haloalkane. Next, determine which among the pair of compounds will exhibit the physical property at a higher temperature. So for the first pair, we're asked to determine which among them would have the higher boiling point. So here, they have the same number of carbons in their chain. The only difference would be the molar mass, the atomic masses of their halide parts. So structure 2 has the higher molecular weight or molecular mass. And that means that this structure would have the higher boiling point. For letter B, again, we have a pair of chains having equal number of carbons in their structure, except that this one is saturated while this one is unsaturated. So in general, unsaturated molecules are bent, while saturated molecules are generally straight-chained and would therefore have a larger surface area and in turn would have stronger IMF and a higher melting point. Next, we're asked to determine the haloalkane substrate from which the given product of a specified reaction is derived. So here, we are given the products and it is signified that this reaction is an elimination process. Therefore, these double bond here, the double bonds here in the products would have come most likely just from a single reactant. And if the double bonds are located on this bond and this bond, then the halogen would have most likely been attached to this carbon here. Also, notice that the other product is Hi, therefore, the halogen atom here would be iodide. Next, for the next reaction, we are given this product and an NaCl. And it was specified that this reaction is a substitution reaction. So here, we're basically just having the same parent hydrocarbon and replacing this part here with the chloride group, the chloride halogen. Okay, so that ends the lesson. I think that we have accomplished this target, which is to familiarize with the physical and chemical properties of halogen derivatives. So this lesson does not include predicting whether a specific substrate is going to undergo elimination or substitution. Rather, this lesson only allowed us to familiarize ourselves with both of these different processes. That question or that concern is probably going to be addressed in succeeding lessons. So if I'm going to make a video on that, please check that out. So that ends the lesson. Again, I hope that this has helped you digest module lesson 2.9 on halogen derivatives.